Right, okay, I'll restart. So the recording actually has the introduction. So runtime coding for OpenFOAM. If you're working in any open source library and you open source code, one of the big benefits is the ability to change the coding. You can go in, you can rewrite any parts you like and recompile. But OpenFOAM is quite exceptional in that the design of the code makes easy. And one of the aspects here is that the authors of OpenFOAM have used the structures in C++ to create this whole high-level meta language which we can use to write our own CFD applications. And if you look online, there are quite a few tutorials showing you how to do this, how to add a new equation into an existing solver, how to write a solver in the first case, and how to do things like how to write a boundary condition derived from the base class there, so it gets compiled as a shared object library and is available at runtime. And this is all very useful, but comes with a certain amount of overhead. And a couple of years ago, I became aware that there was quite a lot of this functionality which you could actually make use of at runtime. So you can actually put code into various of the case files as appropriate. And when you run any of the OpenFOAM executables, even ones I presume you write yourself, it will compile that code and make it available. So I thought, hey, this is great. I've been playing around with it a couple of years, and I thought doing a session on this would be quite a nice idea to bring together some of these concepts and to show you how this could be used. The programming language is the same as for writing your own application, so I've kind of vaguely assumed that you're going to have some concept of knowledge. So I'll back up a bit about this. What can you do with this functionality? Well, there are at least three things here. You can use it to provide your own coded boundary conditions, and I'm going to start by showing you how that works. You can also code function objects at runtime and provide additional source terms in the equations. So what I'm going to do here is to show you how this is done, at least to start off with by example. So I'm going to walk you through how to provide new boundary conditions and then go into a bit more detail about how this is done underneath and what sort of functions are available. I'm assuming that you've possibly had some programming experience, and I just realized Tess has joined us and Matthias is here, and I have a horrible feeling they probably know more about this than I do, so I might actually forward questions to them from time to time. But I'm going to assume we've got some understanding of how to do this in the code. I am going to start off with a review of how we code in OpenFOAM. Obviously, a full introduction to that would be probably several sessions. If you haven't tried it, I'm hoping my explanations will be sufficiently detailed that you'll be able to follow what I'm doing. And as I say, there are lots of tutorials out there, some of which I've written actually, and if you follow them up afterwards, maybe this will start you on a wonderful new area of programming, basically. So, first few slides about OpenFOAM programming. I admit I've nicked a lot of this from my undergraduate teaching. I always say that OpenFOAM can best be treated as a special programming language for writing CFD codes. A certain amount of this is inherited from C and C++, but the authors have used aspects such as classes and templates to provide essentially additional variable types to manipulate data that we're going to use. And this ranges from simpler things like higher level data types, things like dimension scalar, a value with its dimensions and a name, finite volume meshes, obviously, fields of scalars, vectors and tensors, and right the way up to chunky objects like matrices and even solution classes. And I'm sure even if you haven't done any programming, you interacted with the mesh, obviously, you've interacted with fields and things like that in practice, so you might get some ideas to how we're doing this in the coding. Now, C++ has its own set of basic variable types: integers, floating point numbers, characters. OpenFOAM adds a number of additional classes. There are some which essentially mimic these. So label is a string, scalar is a double precision floating point number, but there are also things like dimension scalar, which I've already mentioned, a vector, a three-component tensor basically, a dimensioned vector, and so forth. There are various storage classes. Now, these days, if we were rewriting OpenFOAM, we'd probably use the standard template library here, but at the time that really wasn't an option. So various of the storage classes have been implemented from raw. Then you've got what I like to refer to as geometric field, because that's how it's used as for scalar, vector field, and tensor field. Finally, there are a number of really quite sophisticated objects, time, database, IO object, which we need to know about in order to control the operation of our codes. Ignore FE matrix, I'm not going to need that, so I'm going to stop at IO objects. Yes?
What is an example of a storage?
Also, the question is, what's an example of a storage? Well, I'll come to that in a minute, but you can have things like singly linked lists. So it's a list of values which are linked by pointers and which is therefore extendable. Not available in C++ unless you're using a standard template library implemented to give us something which can stretch, basically. So, here we go. We've got a number of classes for creating and addressing memory at the basic level. And this is a list, which is a simple fixed length structure of data, but also pointer list and singly linked list, which are variable here. And these are what are called template classes, so they can be declared for any storage type. And if you look in the code, you might well see something like list of labels, sum list. So that's declared a variable sum list, which is a list of labels, which might be, I don't know, boundary conditions or boundary patch names or something like that. We do this so often, but actually often this declaration here, list of labels, is in fact alias to label list. So if you see something called thing list, it's a list of things. Now, one of the basic things, aspects we need to do here is to be able to communicate from our application to the user. So we need to be able to write out to the terminal. And in C++, this is done through streams, an object that you redirect output to. OpenFOAM, exactly the same, but its own version. So if you look at the code, you'll see things like info, redirect a string like this, which basically writes out time equals and writes out the value of the time and then puts a return character there. I'll come back to this statement here, but it's quite interesting in a minute. Now, that's one thing. Obviously, we want to be able to communicate with the user, but the other main thing we need to do is to be able to read in and write out data to disk, often quite large data. And this is controlled by, first of all, OpenFOAM provides an object registry. So every time you create a large object, a field, a mesh, or anything like that, it gets registered with this database. And if you know how, that enables you to access it anywhere in your code and manipulate it and make use of it. In order to do this, every time we create an object, we use something called IO object. And this defines the behavior of the object when it's being created, when it's being destroyed, and what happens at each time step and what happens every time we want to write out to the disk. So you'll probably remember that, or if you've done any coding, when you program one of these objects, you need to specify what to do when it's created or read. So must read, read if present, no read. And equally, what happens at write time? Do you write it out or do you not write it out? And the top level object registries associated with the time class, and each program has an instance of time. It's usually called runtime. This controls the time stepping during the OpenFOAM simulation, and you can query it in what is the standard C++ method to provide information. If I go back a slide now, that's exactly what I've done here. Here's my variable runtime, my time instance here. I'm accessing a function, part of that class called time name, and that returns the name of the current time that we are in the simulation. Other access functions here, time step, directory name, write, and things like start time and end time. These are all fairly obvious, I think. Next level, what about the mesh? Well, all of our mesh information is held in an object of class FVMesh, finite volume mesh. And this is constructed when we start a simulation. If you look at the output to disk, when you run a program, you'll see that one of the first things it does is to create all of this mesh information. Basic mesh information is points, faces, cells, and boundaries, but it also has a lot of information about indexing and so forth. It's read in, well, you know all of this basically. Finite volume mesh is also responsible for changes due to mesh motion. Now, this slide is what I use with my undergraduates. The next one, I thought it would be worth going into a little bit more information here from the point of view of the programming. So, this is a very crude inheritance diagram. It's not precise. I didn't pull it out of the documentation. I just put it in to give a sense of some of the relationships here. The basic mesh type is something called primitive mesh. That deals with the basic topology, what joins to what. Inherited from that is a class called polymesh, and that deals with the geometry, the points, the faces, and so forth. And then derived from that is the class we actually interact with, FVMesh. That provides the additional functionality necessary for the finite volume method, including things like the mesh motion. Now, one part of polymesh, so this is, I think, a has a rather than is a relationship, is a class called polyboundary mesh, which is basically a list of boundary patches. There's my list storage patch there. And that's going to be quite useful, obviously, if I'm going to be writing anything to do with boundary conditions. I obviously need to be able to access those boundary conditions. By the way, I'm trying to go through this bit as quickly as possible. If there are any questions, just stop me and I'll try and explain in more detail. Anyway, mesh access functions, again, these are part of the class, part of the FVMesh class, or possibly lower down, and enable me to access things to do with the mesh. So I can ask for the cell's volumes and centers. That will be a number, that will be a vector. So we're getting back vol scalar fields and vol vector fields. Do the same thing for faces. So I can ask for face centers, face area vectors, and face area magnitudes. I'll use some of these in the examples in a minute. Now, another class which you probably all you have all interacted with, because it's the basics of any CFD code, are things like vol scalar field and vol vector field and so forth. And these are based on a template class called geometric field, which is, well, the technical term is instantiated. We create it on the different basic types, scalars, vectors, and tensors, and so forth. Geometric field provides things like dimension checking, automated. It also provides access functions for boundary and internal values, and provides us with the basic algebraic operations as appropriate. So vol vector field has the possibility of taking a dot product. That's obviously not relevant for vol scalar field, so it's not available. And if you're programming, the one thing you need to watch out here is this is overloading commonly used symbols in C++. Unfortunately, the one thing we can't change is the order of precedence, so it isn't always what you would expect mathematically. So you sometimes need to provide brackets to make it actually work. And again, I've put in a little bit more advanced material here in terms of what's in the library. I haven't provided the entire inheritance graph here, but the basic type here is a field of things, scalars, vectors, whatever, which provides us with the basic algebra together with the operations, operator functions. Derived from that is a dimensioned field, and that adds the concept of dimension checking to all of these operations. And then finally, geometric field, which is vol scalar field and so forth. That gives us access to the internal and or provides us with the internal and boundary fields. I didn't like the way I laid out this slide, but it gives you some ideas to the functions which we're accessing here. Geometric field, we can ask for the internal field, we can ask for the boundary fields. Dimension field level gives us dimensions, obviously, the mesh reference and various operators with dimension checking, and those are built on the fundamental field algebra operations there. Plus, minus, multiplication as appropriate, but also things to access components, x, y, and so forth. Okay, so that's hopefully given you a quick overview of what I'm trying to use here. If you already know C++ programming, I've just reviewed it. If not, hopefully that's given you enough information to follow what we're doing. So I thought I would start off by talking about the runtime programming by showing a couple of examples of things to do. And one thing, so I went to the tutorial directory and pulled out hopefully a useful case. It's in the tutorials. It's the elbow case, runs with OpenFOAM, and it's a recreation of a fluent test case, which has a flow coming around this right-angled bend at 1 meter per second inlet velocity, and a secondary injection here, smaller duct at 3 meters per second. So I'm going to hopefully run this. So I'm in the elbow, I copied it across so I can do usual all run. There we go. Doesn't take long to do. So there's my geometry. Let's have a look at the velocity, which is 0 at the moment, but if we go to, oops, there we go. You can see the flow developing to 10, time step of 10, where hopefully it's reasonably fully developed. So what I want to do now is to change this boundary condition using this runtime coding in order to make it pulsatile. I want it to change from 0 to 3 meters per second, or rather from 3 meters per second down to 0 and back up again. This is what I've got here. I want a time-varying secondary inlet of this form. So I chose to use a cos squared function because it goes between 0 and 1, basically. So I'm not going to get negative flow at any point, going up to a maximum of 3 meters per second. And actually, I'm going to do it at from t equals 10 onwards. So t minus 10 will be the form here. And that should give me this pulsatile thing. And how does this work? Well, this is where the runtime coding comes into. And obviously, a boundary condition is going to need to go into the velocity. So let's have a look at that. Now, I've been a little bit naughty. I'm obviously not going to write this interactively. I've prepared one in advance, which we can have a look at, called a U-pulse. This is my velocity inlet. Okay, so this is taken at a time 10 here, so it's got an internal field which is hopefully fully developed, and if you scroll down we get to the boundaries here, and we've got an entry here, velocity inlet 6, which is my small inlet, and in the standard case, it just gives a fixed value and a value here. Now I'm converting it to a class called coded fixed value. And this is one of these coding classes. Standard introduction here, there's a value, which in this case is pretty much a dummy. We're going to write over it, but we need to have the keyword in there. Next thing is a keyword called name. I'm developing my own boundary, so I want to give it a name, and I'm going to call this oscillating inject. And then this type of boundary condition, this coded boundary condition, wants some code. So this is what's here. I start with a keyword code, and then everything between hash, open brackets, hash, close brackets, semicolon here is code in C++ using OpenFOAM nomenclature which will be compiled at runtime. So when I put this into my, when I introduce this into my time step 10 directory, and restart the code, it will read through this, it will compile this into actually a shared object library, I suspect, which will then be accessible when it's doing the run. So how's it working? Well, obviously I need the time. Pretty much every object knows about the database. So this is the current object. DB gives me the database, and I can ask for the time from that database. Now that's going to be in the form of an OpenFOAM object, which is going to be a bit complicated. I actually just want the value, so I ask for the value, and I've assigned it to a scalar t. So that's my time, the time in the simulator, the time of the time step we've got to, whatever it happens to be. Now I want to create a value, which is just going to be one value for this. So if you read through this, you'll realize this is exactly what I gave in the slides here. So I'm working out this cosine here, taking the square and multiplying by 3. It's a vector, so I'm assigning the y component here. The x and the z are still going to be 0. And then I need to allocate it to the boundary, which I can do using this assignment operation, and that will put this value at every face on the inlet patch. Now this is where it's probably going to start going wrong, because I thought I would try and do this interactively, which always doesn't work for me. But if I cp upulse into, I have got this in another directory all worked out. So if I screw it up, I'm going to switch to that. Okay. Go into there. So I'm going to remove U and move U into its place. I obviously need to change control dict. I hate doing this interactively, people breathing down my neck. So I'm going to start at 10. That should start from there, shouldn't it? Okay, go to 100, right interval, there we go. So let's see, oops, damn. So this should now run the next 90 seconds of time, which should give me the pulsar bit. So wish me luck. See, what's happened at the beginning is a bit of compilation. So it's actually compiling code, and it's worked, and it's now doing my, the sweat pouring off me is nothing to do with the temperature here. It's thank God that worked. Anyway, it's done the compilation, it's provided the compiled code, which has been read in as a boundary condition. If you look here, you've got all of the time step directories, but we've also got a directory here called dynamic code, which is where the result of my compilation has been put. And if I go into parafoam here, And let's go to okay, there we go. That's the steady state or reasonably steady state bit. And now if I we've got every few seconds, every second I think actually, a new snapshot. So if I play them, there we go, you can see the inlet is now pulsing quite merrily. So am I in the way? There we go. So that is each reading in each time step to 100. Let's do that again when I'm no longer in front of you. I'll do that again simply because I'm really quite proud of myself. So it's going between 3 meters per second and 0. That's my new boundary condition. Now, of course, you can do this in in OpenFOAM, you can do pretty much anything in several different ways. And you could do this by writing your own boundary condition derived from the appropriate class, compiling it to provide a shared object library, linking that at runtime and using it. And that's great if you're prepared to put in the extra effort there, but I think you'll agree this is a much quicker way of doing things and much lower overhead to it. Yes.
Could you please go back to the file for the velocity?
Yes, in fact, I have actually. Hang on if I can. I am. I was actually. There we go. That's the relevant bit of the thing.
So the confusion for me is in the type. Because if the boundary condition type is a coded fixed value,
yep.
Is the fixed here fixed in space?
The fixed value simply means you are specifying the velocity as against specifying the gradient, basically. So it doesn't have to be spatially constant. You could, in fact, I'm going to show you in a minute how to do a spatially non-constant one. But for this, I wanted to change the inlet values with time, so I made it simple in terms of the space.
So fixed value refers to fixing the velocity information.
That's right, yes.
Thanks so much.
Yes. Okay.
You answered my question in terms of spatial notation.
Indeed, thank you. Yes. Yes.
About the value uniform, you said that it's a dummy.
It's essentially a dummy, yes.
We can't use it inside the code, for example, to fix the 0 is 0.
I would presume that when it's read in, it probably sets it up. But of course, I'm overwriting it lower down. I'm not 100% sure about that. I'd test that before doing it. Anyway, so a little bit more detail now. I've already said most of this, but if you look inside the code, you find that this new type, this coded fixed value FV patch field class, derives from, it's what they record an example of multiple inheritance. It derives from 2 base classes. It is a fixed value FV patch field, so it's derived from the base class for boundary patches. So it is going to be a boundary patch, but it's also derived from a class called coded base, which is the base class for all runtime coded classes. I've said most of this already. The boundary has a usual form, type, a value, in this case it's a dummy value, and I've given it a name, and then this keyword code and the hash bracket bit enables me to provide the code which is going to be compiled. That compilation provides basic functionality by default, so it gives you access to the mesh and to time objects. I'll show you how to extend that in a minute. And it's a class, so there is this keyword this, which gives access to the class object itself. And this enables me to ask for the runtime database and get this time value, calculate the single vector, and set a uniform value using this assignation operator. Now, you want to know how to, sorry.
What does the operator equal sign do?
It assigns that value to the inlet. So it must loop around and assign that value to each face.
Okay, wonderful.
So you wanted to know how to do a spatially varying one? I've done that too. Let's put this at the main inlet. At the moment, it's a uniform inlet here. And of course, if this was a real pipe down here, it would have developed maybe a parabolic inlet profile. So I thought, hey, I'd have a go at that. So let's change it to a parabolic profile. 1 minus y squared, that's my parabola. It took me a bit of juggling to actually find the overall dimensions of the inlet, but it's actually going from 0 to 16 in y values. So I've actually reassigned it to the middle and normalized it to be plus or minus 1. So y is going from -1 to +1, and I picked this value to give us approximately the same inlet flow, volumetric flow, basically. So if I'm going to be setting up to calculate the inlet flow velocities, I'm going to need to find the y component of the face center and then allocate the velocities face by face now. So I'm going to need to loop around all of the faces in my patch. So same basic thing. I've just pulled out the code section here because I'm going to assume you know the rest of it here. And here's my code. So I'm going to be using some of these mesh manipulation things that I told you about earlier. First of all, I'm going to want to access my boundary patch. So it's a class function called patch, gives me access to that. So in order to make this a little bit more understandable, I hope, I've split this down into several sections. So I've called that something called boundary patch. And then I can ask, I can ask for the face centers here for all of the faces making up that patch. So that's going to be a series of vectors specifying the X, Y, Z components of each face center making up the patch. I'm also going to want to get hold of the values in the field. So again, this can be done through the this keyword, which gives me access to the fundamental object I'm manipulating here, which happens to be the field anyway. And then I'm going to loop over all of the faces in my patch. And again, this is something which various template libraries in modern C++ give access to, and things like Python do automatically, but wasn't available when we started writing OpenFOAM, so it's individually implemented here. So I'm going to loop around every face in my patch. For each face, I'm going to find the Y component, and I've modified this to go from -1 to +1. I've calculated an intervening value here, which is my X component, using the formula I gave there, and then I've put it into the field for that particular face, for that particular face in the patch, basically. And again, it's a vector, it's in the X direction, so it's UX 0, 0. And this is going to loop around every single face in the patch and assign the correct value to them. So I could show you that, but I am aware that I'm running a little bit late anyway, so I'll try and package this up as some examples. I've got it, but yeah, that's what's in that piece of code, and I want to go on to the slightly more advanced stuff. So if you want to, I'll provide access to these functions, and you can try them out yourselves when you get home, basically. So a little bit more explanation of what's going on here. The class we're dealing with here is derived from a standard patch class, so has an access function for it. The function CF returns these face centers, and I can find the Y component here. This gives the object itself, which is a field, so I can allocate an appropriate vector to each patch face. And for all is an OpenFOAM defined iterator, so that enables me to iterate over all the faces in the patch and assign them. Now I wanted to go in a little bit more detail as to how this is set up. So I've mentioned this before. My coded fixed value boundary type here is an example of multiple inheritance. It inherits from the base class for fixed value patches, but it also inherits from the base class for all coded base objects. And what we're doing here, the coded base class is, I think, a virtual base class, so it provides virtual functions for things which are going to be implemented. Actually, sorry, the coded fixed value provides virtual functions for things we're going to want to implement here. And where we've got this code word, this is actually one of the virtual functions we're providing. But there are others, and this is how we can give further functionality to this. You don't have to provide these functions for everything in the class, just the ones you're going to use, but there are other functionality which you're going to be able to provide through this mechanism. The inheritance here gives classes with runtime coding inherit from this coded base class, and here's the inheritance diagram for this. And there are a number of other classes which inherit similarly. For example, function object. So that's going to enable us to write our own function objects, and at the same time FV model, which enables us to program and introduce our own source terms into equations. These are all of the derived things here, and these are the three which I want to focus on today. As I say, coded base and the individual classes derived from that provide the interface for what can be accessed and changed through this coding process. One thing you might want to do is to extend the access you're going to be able to provide here. If you just write the code section here, you've only got a minimal access to the OpenFOAM library. If you want more, then there are various code include and code options you can use here, and these enable you to access all the things you would typically access in the make options file. So include files here, which will give you access to the definitions of a much wider range of OpenFOAM objects, and code options, which enables you to link to various libraries dynamically during the compilation process. So that's something which you may need to do if you're going to do anything a bit more sophisticated here. Here, a lot of this I'm basing on Deoxygen generated documentation for the OpenFOAM classes. Is this going to work for me? Possibly not. It's supposed to link up. Nope. Okay, I'll do it this way. Okay, so if you look in, I'll go to version 9. Anyway, if you follow the links I have given in this slide, see the OpenFOAM documentation. This is generated by a program called Deoxygen, which reads through the header files of the library and extracts information about the structure. And this is really useful because it gives us a way of automatically documenting the shape of the library. And if you know what you're doing, it's a little bit impenetrable, but if you keep a cool head, you can read through this and pick up information about what's going on, both in terms of the available functions and the links between the different classes, but also in many instances information as here as to how to use them. So I've in this particular case gone to the class information for coded fixed value FE patch field. So this is the class I've been using here. Various functions here, including the including somewhere here the code bit which I've been using to get this, and down here an example of how to do it. Here's my code to do a particular operation here. They've commented out the code include and code options bit here. As I say, if you're not needing them, you don't need to provide them there. This is one of these examples where the branches, so I've used the foundation version 9 here, but you can do the same thing in the ESI version. The functionality is available, it's equivalent, but there are subtle differences in naming conventions and so forth. So as I say, follow these links, explore the deoxygen information here to get more information. Any questions from anybody so far? There's something on the chat, is there? Is it possible to run in parallel? I do not know. I have not tried that. I would, yeah, was that a yes? That was from Matthias, who probably implemented this. Yes, it is possible. Thank you. Any other questions from anybody? Okay, fine.
When you put the velocity information to the cell face.
Yes, the face centers, face values rather. So.
But then the cell face is a face on the boundary patch.
The boundary patch consists of a number of faces which are the boundary, basically. Each face has a cell center, has a center value, a center location, X, Y, and Z components, and a value. So I'm extracting the location as a vector, finding the Y component, using that to calculate the exact value for that face, and then allocating it to that face.
So you don't need to put the information to the cell center itself.
No, because I'm dealing with the faces which make up the inlet boundary patch. Okay, so I wanted to this point to say a bit about how to, so we've done how to do an inlet condition. Of course, that would do for any boundary patch, basically. What about other examples? I've mentioned function objects, and I guess this is probably the other big use here. You can, of course, again, write your own function object, derive it from the class, compile it, and so forth. But this concept of a coded function object gives us the ability to do that on the fly in the code with less overhead. We can extend the existing OpenFOAM post-processing functionality. The class involved here gives a number of functions to be overloaded. So code read, which is run when the object is basically created, code execute, which runs when the function object is executed, and that could be the time step, or it could be less frequently, every 10 time steps or something like that. Code write is code which runs when particular write operations occur, and then code end runs when the code terminates. So this is an example I created a few years ago for my undergraduate students, and I now extended a bit. It's the Taylor-Green vortex, and I'm sure, is that a question? No, fine. I'm sure we're familiar with this. It's a standard test case in LES. It's a simple case. It's a periodic box, which we start off with a series of deterministic vortices created, for example, by equations like this, sines and cosines, which gives this rather attractive series of velocities here. And those vortices interact and decay, forming turbulence, and it's a classic case to run LES on. So I wanted to provide this for my students. And I realized there were two things I need to do here. I need to be able to initialize this U field, which at the time I did by writing my own code, but I've now come to realize I can do that. And I can also calculate the total turbulent kinetic energy for each time step, which is information I want. So total turbulent kinetic energy is the mean velocity, half the mean velocity squared, plus any subgrid scale turbulent kinetic energy. I'm running the K, the one equation K model, turbulence model here, so I want to include that. And as I say, originally I had this in two parts, a separately compiled code to initialize things, and then a function object to calculate this quantity. But I realized that I could do both of these in a single function object. So I've written a coded function object here, overloading code read to set this up at the start, and overloading code execute to calculate the turbulent kinetic energy here. Now, I haven't included the code directly, so I'm going to have to go into, I think it's Taylor Green 2 was the one which worked. And as with all function objects, it's in wrong place. It's in control dict. So usual place, bottom of the control dict function. I've got various probes and functions and so forth. Here's my coded function object. I've called it ET code. You need to link to a shared object library here to get it to work. It's a type coded. I've given it the name ET code. I'm doing right control time steps. So one of these, the code execute, will be executed every time step. And then I've provided code for code read and for code execute here. Code read is going to be something which gets operated the first time around. So I want to read in my velocity and then set it up. So I write out initializing field U. So I'm telling my user what's going on. Standard method for reading in the field. Here's my IO object. So I'm picking up something which is registered with the runtime database and read in the information here. And then I want to process this. I want to replace the values of the vectors one at a time. And I do this by extracting the X, Y, and Z components, normalizing them. And I had to be a little bit careful because I needed to get rid of the dimensions whilst I did so. And then replacing the X, Y, and Z components with the appropriate values from that equation I showed you earlier. Then write it out so I can store it and end it there. So when I start this, I should get this coming through. And then the other piece of the code here is overloading this code execute module. So here's where I'm going to be calculating my total kinetic energy. So I'm going to set up my own, instead of reading in, I'm going to set up my own scalar field for this. So I've called it ET for total energy here, and I register it with the database, although it's a temporary object, it's probably going to disappear. And then I look up the U and K fields here and take the square of the magnitude of U here and add on the turbulent kinetic energy K here. Now, this lookup object here is a rather interesting one. C++, it's a object-oriented language. The different objects encapsulate, not encapsulate, wall off data and functions. So they're typically private to the use of that particular object. So if you're in one object, you can't necessarily access data from somewhere else in the code. But sometimes in OpenFOAM, we want to be able to do that. And this is one of these places where the runtime database comes into use. If you know what is the name of the object you're looking for, you can look up on the runtime database to get access to that object. So that's this lookup object call. I am looking up a vol vector field called u, and that is going to give me access to the velocity field, which I would not otherwise have access to. Similarly, I can do the same thing for the turbulent kinetic energy here. And then I'm going to be writing out this value each time I do this. So each time I access this function, it's going to print in the log console this line ET, given the time and then the value. And then if I save that, I can extract that using grep and process it appropriately. So let's give it a go. Yep, mesh, that's okay. There we go, it's working. I stopped it there so we can scroll back and have a quick look at it. Again, I've already run this, so it didn't recompile it. It picked up the fact nothing had changed, so it is using the dynamic code. I could delete that and rerun it, which would show you the compilation, but we've seen that. So that was it running the code. It's initialized the field. For some reason, it seems to have done that twice, which I'm not quite sure about, but anyway, it's done that. And then going into the time stepping here, you'll see wherever the heck it's got to, I can't see it. It should have. Yeah. It should have written it back out again. Let me. Okay, this is 0 time step directory U. There we go. So it's written this out again. I am not quite sure why it is not doing, why I can't see where it's written out the it may be, yes. Yeah. It was supposed to write it every time step, but I may have screwed up slightly. Sorry. I will look into that and see if I can rectify it. Sorry about that. Okay, this is why I don't like doing things interactively. They have a tendency to go wrong. I'm nearly at the end though. Okay, here's my slide explaining it. Same in syntax as usual, but I'm so when I'm constructing the, I'm in both cases I'm constructing a geometric field, reading in the velocity and modifying it, or constructing one new for the turbulent kinetic energy. Syntax is exactly the same as we do when we're programming, but we don't have access to the mesh object, but we do have access to a call to the mesh object. So that's a call which gives us the mesh object. And if I'll just yes, whereas normally we'd have mesh.time.time name. I've now got mesh function call.time.time name, simply because I don't have the mesh, but I have access to it. You probably could, yes. Yeah, that's a good point. I could, that might be part of the issue, but it was working. So. Yeah, I'm using the replace call to update the velocity vector components, and just say lookup object gives me access to the named objects of the field from the runtime database. And you're right, I could probably have done that more elegantly, but I was just demonstrating this. That's really the end of what I wanted to show you. If you want to look at a more sophisticated example here, and yes, this is a piece of unashamed self-propagandization here, but I've recently published something in this new OpenFOAM journal, and I can show you. I should be able to. This would better work. I'd be very silly if I can't get. Here we go. Implementation of modified lid-driven cavity case. I'll download the PDF. I'm not going to go through this in detail because it's quite mathematical, but I saw there was a training session parallel to this one on method of constructed solutions. And I'm pretty sure this is an example of that, because what this is a lid-driven cavity case. So it's a square box with one moving wall, but it's one for which there is an analytical solution. Got an analytical solution because they have two things. First of all, there is a body force inside the cavity, and secondly, there is a non-uniform lid velocity. And that also gets rid of the problem in the corners of what's the velocity, because it follows this pattern here from 0 up to a maximum value and then back down to 0 at the corner. That's the wall velocity. There's a body force here, and the code is available from the OpenFOAM journal website, as well as the information here. So I've included it in the text here, the different user-coded examples, but it's also available for download. And I'm making use of a number of features here. Obviously, the moving wall itself is a user-coded boundary condition. The body force is implemented as a user-coded FE volume, whatever it is. So further down, coded source, here we go. So I'm using the coded source here to introduce a new body force into the momentum equation. And then I'm also using, that's a different bit here, a coded function object here to evaluate the true known solution and to compare, which is P theoretical and U theoretical, and then comparing that with my calculated solution to get the error out of it. So this is quite a sophisticated use of this coding ability here. If you're interested in taking it further, it might be worth having a bit of a look at that. So just provided the link, or rather the reference there, and a few details here. I've put in the spatially varying boundary condition there, for example. Oh, sorry, this is the coded FE model to add to the momentum equation here. Actually, there's an include here. It's actually a lot larger. There are about 20 lines of code going in there, which I needed in several places. So I put them in a header file there. So there we go, conclusions. This runtime programming facility provides a range of additional features. You can use it to implement boundary conditions, both fixed value and mixed, so including gradient conditions if you need them. You can use it to code your own function objects and use those, and also source terms and equations. Something I didn't mention here, but OpenFOAM has various functions available, and you can use this to create your own templated classes. I didn't want to go into detail there because I haven't done it yet, but that's another possible option. And as I say, the syntax for doing this is exactly the same as standard for OpenFOAM programming, so it adds considerably to the power of the code. Any questions from anybody? Yes.
When you do the Taylor revoke example,
yep,
you create a variable to store the turbulent energy.
Yes.
So I imagine that the function object itself allocates the memory.
Yes. Yeah.
Does it also destroy the memory again afterwards?
In the way I've written it, yes, I think it is doing that. I was after speed in writing it rather than elegance in implementing it. It's not a huge box I'm running it on. You saw how fast it was running. I didn't worry too much about code efficiency. I think, and Matthias can probably correct me if I'm wrong here, I think I could probably create that ET more globally in the code read function, and can create it once and access it in the code write function, and therefore not have the overhead of constantly creating and destroying it. But I didn't, because I got it to work and stopped at that point. No problem. Anybody else? Yes.
The function, and then you say, explain that patch. You include all of this in that function. There's one function, the function that you want to average.
The way I've been using this, yes, I am hard coding the exact details each time. I guess you probably could create one which read in a dictionary somewhere. I mean, that's standard OpenFOAM thing. You can create a dictionary object, and maybe it's actually a dictionary already existing, so you access it using lookup function, and you could go in, pull out particular values and use those in your function object to in that case you would have a function object which would be controlled out externally. You could change the values, you could create several and have them do different things. Yes, I don't see why not. You know if it works. Matthias.
Just a little remark. One thing I find very useful for is if we implement something for a client.
One moment, Matthias. Matthias, can I pass you the microphone?
Okay. Yeah, so just a remark. Or clients in the next when it's going to be around. This is basically you fire off and you can forget about it. Spit me.
What you mean is you write that and then it's so that your client's problem, not yours, right? Thank you, Matthias. I thought that was important enough to make sure it got recorded. Any other questions from anybody? I see there's been a bit of a discussion in the chat. Yeah, is it possible to combine spatial and temporal values at the inlet patch? Yes, and Sarita said yes, that is the case. I mean, I've written them as separate bits, but there's absolutely no reason why I couldn't have, for example, taken the inlet parabolic profile, extracted the time and modified that profile by the time, and then I could have had an oscillating and spatially varying boundary if I wanted to. It's just that I find, certainly when I'm teaching, it's best to isolate the different bits of the problem. So yeah, exercise for you guys as students, take my code and combine those two bits and have an oscillating spatially varying boundary condition. I'll see you next year. Right, well, thank you very much. I guess that's probably time for lunch. Yes, I've overrun, sorry, I've delayed you from lunch. Have a good lunch.